Hi, this is Peter with CalcBook, and today we're going to be looking at another shear flow calculation. This time we're going to be looking at a built-up T-section. So again, right, we're going to be using AISC 360 chapter J2 for our weld capacity. So if we have some, shear diagram here and our T-shape, right, we are going to be calculating the shear flow demand, small q, which is VQ over I. And in this equation, right, V is just going to be the shear demand, so the point along that shear diagram that we're evaluating. And then Q is our first moment of area. So that basically, right, is the area of the section of interest or above the section of interest multiplied by the distance from that section's centroid to the centroid of the overall shape. And then I is just the moment of inertia of the entire section. So let's take a look at our problem statement, right? We have a built-up T-section, an overall depth of 18.5 inches, a web thickness of 0.45 inches, a flange width of 7.5 inches, and a flange thickness of 0.55 inches. Our loading, right, so from our shear diagram, we have a dead load shear of 35 kips and a live load shear of 55 kips, and we are going to be determining the minimum fillet weld size required using the LRFD design method. So let's go ahead and open up CalcBook, and we'll get started on the design. All right, we've got CalcBook open now, so we're going to click into our steel design module. We can select the 16th or the 15th. We'll go ahead and use the 15th edition. We'll click on our connection design. We'll toggle over to our welded connections and scroll down and use our shear flow design T design module. And we're going to be using US customary units. So click continue, get that loaded up. Okay, so now we can go ahead and enter in our geometry for the shape. So we have a depth of 18.5 inches. We have a flange width of 7.5 inches, a flange thickness of 0.55 inches, and a web thickness of 0.45 inches. And so the problem statement asked us to determine the minimum size weld, so we'll leave this at 1/4 inch right now, and then we will adjust it later to optimize our design. So let's click over to the demand. We are going to be using AISC 716 load combinations. Our vertical shear in the profile we said was a dead load of 35 kips and a live load of 55 kips. Okay, and we are showing that we have a DC ratio of 0.65, so there is some optimization that we can do. Let's take a look at our calculations first, and then we'll come back and adjust that. So our demand on the weld is just going to be based on our section properties, right? So we want to actually solve for our little q, our shear flow demand. So we get some of our properties, our areas of each piece of the flange and the web. We calculate the distance from the bottom of the section to the centroid of the flange, and the same thing to the centroid of the web. And then we calculate our y sub c, right, so the distance to the neutral axis from the bottom of the shape. And then we calculate our q, right, the first moment of area. So like we said, it's the area of the piece of interest. So in this case, it's going to be that interface between the flange and the web. And it's the area of that component multiplied by the distance from the centroid to the centroid of the entire shape, which gets us 25.26 inches to the third. From there, we calculate the total moment of inertia of the shape, of the T-shape, and then we can calculate our little q, right, our shear flow, and we do that on a per linear inch basis, and that's just the VQ over I, which gets us a demand of 7.29 kips per inch. Then we can go ahead and calculate the capacity, and remember we have two welds, right? We have a fillet weld on each side here, so we want to make sure we account for that. So we have 2 times W divided by square root of 2 for calculating the area of the weld. We run through our AISC weld capacity, and we get a capacity per inch of 11.14 kips per inch, which again gives us a DC ratio of 0.65. So we can go back to our capacity tab here, and we can start reducing the weld size to see how efficient we can get our design. So it looks like 1/8 is too small, so 3/16 gives us a DC ratio of 0.87, which is acceptable and within the limits. So that is a shear flow design in CalcBook for a built-up T-shape. We hope you enjoyed the video. If you have any comments or questions or want to see other designs, please let us know in the comments below, and we'll see you next time.